Okay, welcome everyone for this video in which we are going to talk about a very special kind of semiconductor devices, which are called power semiconductor devices. So we would look at in next 10-15 minutes that what are these devices and how does one design these devices, right? So what is the first of all you have to understand why there is a need for a special kind of device. What does it serve? So if we see from an application point of view, what it serves as a purpose is, first of all, if we see when we say power itself, that there is in the name itself, there is a power. That means you are going to use these devices typically at higher voltage or power rating, right? So that these devices are going to be used at higher voltages or higher power ratings, right? Because we know power is your current into voltages. So if you're using at higher voltages, there's a certain current also which is passing. So that is also higher power ratings. Now, where is that going to be used? So typically, this is where you will find the different, based on the voltage, this can be further divided into different bands, right? And that is what you would see. So there would be a band where you could see maybe you 10 to 50 volt. So similar to that, there are multiple bands of these power devices which you will see as high as more than 1000 volts, right? Now, so that is what one thing which you have to understand when you are working in the power semiconductor devices or you are interested in power semiconductor devices. You have to first understand that which range or which voltage or power range am I going to look at, right? Because one device may not fit all. That is one of the key things which you have to understand, because the requirements based on the voltage, efficiency, the things in the application could be very different. For example, if I am looking at the lower voltages, let's say like 5 volt to 50 volts, these lower range, this even till 5 volt, you see that there is a power devices which are there in your laptop also, right? Because there is something called which are PMIC or power management IC, which is using MOSFETs or some kind of a MOSFET, which is a power device in itself, right? And we'll see what kind of architecture that can be. Then there are other applications where, let's say, let's look at the extreme where you are really looking at very high voltages. This could be, these higher voltages could be, let's say, in the EV vehicles, right? Where you have much higher demand from the voltages, right? And so that means you are looking at something as like power converters. So power converters means you are now really interfacing your electronics or whatever intelligence you have to higher voltages, where you are actually driving the whole system like a car, right? So you really need very high voltages where you need this conversion. So conversion means this could be DC to DC conversion, right? This could be DC to AC conversion or AC to DC. There are multiple application of this conversion could be. So now the question comes, okay, yeah, this I understand that there is a higher voltages I would require. So what do I need to change in my device which you have been talking about? So you have been talking about something which I've been seeing as a switch, right? Which is our MOSFET, which is what we have been talking about. Now, you are saying that this MOSFET may be something where you can see that it cannot operate for very high powers. And why is that so? First, let's understand that. Why is this MOSFET not able to operate at high power? So that for that, you need to probably, this symbol cannot explain that. You have to look at the physical structure, which is what we do, that you look at the physical structure of this MOSFET, where you have a semiconductor, right, which is the substrate or base on which you are making this device. You have a metal oxide, which is the main control knob which you have to control the charge in this device. Then you have your drain to source field, which are important units so that your current you can control the current which is flowing in the device, right? So which is your source to drain terminal. Now the question is, okay, and then we also saw that if we are, let's say, making a device for electron conduction, we may need to have some pockets here which are filled with some electron charge, which we can call it N charge, right? N means there are a lot of electrons. Similarly, here there could be pocket which could mean N. So now, based on the VG or what voltage we apply, we are able to switch that. That is what we have already seen in one of the video, that how the transistor operates as a switch. Now the question is, when we want to operate at higher voltages, what happens? And which higher voltages am I talking about, right? So then you would see that when we are talking about typically higher voltages, we are talking about this voltage which we are going to apply across this VDS, right? That is the voltage we are talking about, which is your VDS. So that means when I am applying or putting this MOSFET in an application such as power converter, or in a different, basically there also it is working like a switch, but the voltage range is quite high. Let's say the voltage range is around 100 volt. Now, if you put this at 100 volt, what is going to happen? Let's see this MOSFET. What is going to happen in this MOSFET? So first of all, for doing that, we need to know that what is the length also of this MOSFET which you are considering. For example, you could say, okay, I am considering for a, just for example, I am maybe considering a MOSFET which is of 1 micron length, right? So if it is of 1 micron length, then let's say when you apply a 100 volt, what is going to happen inside, right? So when you see that there is, obviously when we are applying a very high voltage, there is a very large field which you are going to see from left to right, right? This is the very high field you are going to see, and this field is coming because you are applying a very high potential difference between the two. Very vaguely, we can just approximate this field to be, if we are applying 100 volt and the length of the thing is 1 micron, then you can calculate that, okay, how many volts per meter this field would be, right? So that would be, so if you calculate this, this would be 10 100 into 10 power 6, or let's say that would be 100 megavolt per meter, right? And if I write it in centimeter, this would be 1 megavolt per centimeter. Now, is this a very high field for your semiconductor like this? And then you will see, yes, it is going to be a very large field. And what is going to happen at this field, when you see such a large field, and this field is typically going to drop across, because you have this typically the semiconductor which we have, let's say if it is either a p-type or very mildly doped, right, or even if it is intrinsic semiconductor, right, you see this portion where, because your body is grounded, or where you have applied to the source, right, this is the typical configuration. So then you will see that what is going to happen here is that this depletion region is going to increase, and this is something we'll talk about in some other video where we talk about PN junctions, what is happening. But what is happening here is that you apply such a large field, it has to drop somewhere. It could drop across the channel, but because there is in between, there is a intrinsic, so that means there is an N here, and then there is an intrinsic channel. So that means now you are going to see that there is more and more depletion region which is going to come as you increase voltage in your intrinsic region. And what is going to happen due to that? Due to that, there is a very large field which is going to exist in this depletion region, right? And what happens when this field is increasing? So then you have to see what is happening to the electron. So then if you imagine this, that this portion, what is happening here is, obviously these two are just like this is same lattice, just that we have, so if I represent these with silicon, right? So in an intrinsic, you don't have any doping. That means all are silicon, right? All will be silicon. While in the P-N type, you will see you may have phosphorus or arsenic in your one of the dopant, right? So this is a very simple bond model one can draw. This is your intrinsic, this is your N type. So now what is going to happen? You are applying a very large field between these two, which is mostly dropping across I, because the resistance is high there, right? So then what is going to happen because of that, that these bonds, because they are already vibrating because of the temperature, but what is going to happen is because of this energy which the electron, so there is an electron which is going now from the left to right, right? So this is how the electron is going into the system, because electric field is that way. So what you are going to see, because the electron is going to gain so much energy into this electric field which is there, it is going to hit these atoms. And this atom, when it is hitting, because there is a very large energy into this electron, it is going to break this bond. Okay. So this bond, because of the just that there is so much energy in the electron, it is going to break these bonds. And because of that, what happens is there is another thing which we see, that there is a electron hole pair, because these bonds are also connected with, there is an electron here, similarly there is electron here, there's electron, more electrons generated, because when two electron came, valence electron, then only this bond was there. So now because the bond is broken, there is another electron available. When the electron is available, these electrons will also see the same field, because they are also in the intrinsic region, and then they will also gain energy and hit another, right? That again gives another electrons, right? So this bond, if it is broken, then other electrons are there. And this is the phenomena which we know as because there is a multiplier effect which is happening, right? So this is the multiplier or multiplication effect. We know this effect as a avalanche, right? That there is an avalanche of electrons which are arising in my semiconductor, and they are hitting because the electric field is available. They gain so much energy from the electric field, they hit every atom. And that is what is going to result into that that you have so many electrons here, which basically means that the very large current is going to flow and your device, so that would disrupt the operation of the device, right? Because the operation of the device was to behave like a MOSFET. Now there is, because of these things, there is a very large current flowing at that field. And that field is what we know as the, because this is similar to a breakdown. So this thing is what we know as the breakdown field or breakdown voltage, right? One can calculate. So breakdown field is something which, because the field is resulting into this, voltage is the quantity which you apply externally, which results into a field, and this field is what is resulting to this disruption. So that is what we know as the critical electric field of these transistors or these MOSFETs, which result into this avalanche or breakdown phenomena, right? So then you saw that, okay, these transistors are definitely something which are very important, that if I were to use this transistor at higher voltages, I may need to either change the structure in a way that the field at some portions do not increase such a high field, right, where this is happening under this region, so that I can drop the field or I can drop the voltages so that the field is not high there. Either I do something with the structure, that is one approach, or you could say I could choose a different semiconductor, right? So this could be an option to increase this. Sorry. So what we want to do is to mitigate this. You may choose to go for different architectures, or you may say that I may choose a different material, different semiconductor material with high EC, right? So with higher critical electric field, so that even if the field reaches very high, I don't have this broken bond. And this broken bond means because the bond strength should be higher in this material. That is what will stop this material from that, okay, the electron is hitting, electron is always hitting, right? That is how the scattering in the semiconductor is. But the point is that because the electron has gained so much energy from the electric field, and if the bond strength is very weak between these atoms, let's say either silicon or other material, then what we are saying is in those material, this bond strength should be stronger so that the EC is higher, right? Other thing is the architecture, and that's based on this. This opens a field in itself where we can talk about different kind of power semiconductor devices, right? What different devices are there, and that you can have a look. For now, I can just give some terminology, but we will talk about them in different videos, right? What these devices are. So for materials, one can consider these materials as something as silicon carbide, gallium nitride, right? Like that. So these are material with higher EC or higher particular. The different architecture one can talk about is your LDMOS, so which is literally diffuse MOS. You have VDMOS, which is VMOS or vertical MOS, right? It is. So there are multiple structures like that which are made basically in that way that you can have the field drop across the structure. You can drop that voltage across the structure so that you have lesser field in the at the junction where this thing is going to break the crystal. So with that, I would stop here, and happy learning to all of you. And if you have more questions, please post it so that we can deal with each of the devices also separately.